You discovered the vertex form in class, and you realized that a quadratic can be written in the form f of x equals a times x minus h all squared plus k. And that the significance of this form is that it gives us the coordinates of the vertex, because the vertex lies at the point whose coordinates are h, k. Now a is the stretch factor. And it's the stretch factor that the curve of y equals x squared is subjected to give us the same steepness of this curve. So what we're going to do now is we're going to convert quadratic expressions from the general form to the vertex form, and later we're going to sketch them from the vertex form. So let's start by attempting to convert x squared minus 6x plus 7 to the vertex form. First of all, what we do is we take the first two terms, the x squared term and the x term, and we ask ourselves, what constant do I need in order to make this a perfect square? And as you remember from the first unit, we have the coefficient of x that gives us -3, and we square it, giving us a positive 9. So we add a 9. However, we cannot just add a 9 to an expression because that will change it. So in order to undo what we have just done, we subtract it. And here's our 7. Now, we actually added a 0 to this expression, so we did not change it. But if we split the expression here, what we have on this side is a perfect square. And this perfect square can be written as x minus 3 all squared, and minus 9 plus 7 gives you a minus 2. So obviously, this is the expression whereby if this was f of x, this would be a parabola whose vertex is at 3, -2. Let's take another example. Let's say that f of x was 2x squared minus 12x plus 5. Again, what we do is we consider the first two terms. And what we did earlier, which was completing the square, can only be done, actually, it can be more easily done if the coefficient of x squared is 1. So we take 2 as a common factor only from the first two terms. This leaves us with x squared minus 6x inside the bracket, and here's our 5. Now we can complete the square inside the bracket. 2 times x squared minus 6x, and what do we need to add to make it a perfect square? And obviously it's a plus 9, because you're squaring half of the coefficient of x. But be very careful, we did not just add a 9, because this 9 is multiplied by 2. We actually added 18. We added a 2 times a 9. So what we should do is that we should subtract an 18. And here's our 5, unchanged. So we added a 9 multiplied by 2, we subtracted an 18, and that means that we did not change this expression at all. Now this is a perfect square, so we can write it as 2 times x minus 3 whole squared minus 13, and this is the equation of a parabola whose vertex is at 3, negative 13, and that is stretched by a factor of 2 compared to the curve of y equals x squared. Our third and final example is the following. Let's say that f of x is equal to negative 3x squared minus 12x minus 5. We take the negative 3 as a common factor from the first two terms, giving us x squared plus 4x, and here's our minus 5. We consider completing the square inside the bracket, and we have to add half the coefficient of x squared, so half the 4 is a 2, and when you square it, it's a 4, so we add a 4, but we're actually adding a 4 inside the bracket, and that 4 is multiplied by negative 3. Negative 3 times 4 is negative 12, so we're actually subtracting 12, and in order to undo that, we have to add 12, and here's our negative 5. So this becomes negative 3, and this is a perfect square, written as x plus 2 whole squared, and this is a plus 7. So this parabola is first of all reflected in the x-axis. It is stretched by a factor of 3, but then it's translated so that the vertex is at negative 2, 7. Now let's sketch a parabola from its own vertex form. And let's take the three equations that we produced in this video. The first one was f of x is equal to x minus 3 whole squared minus 2. And let's put our axes here and see what we can do. The vertex is at 3, negative 2. So if this is 3, this is negative 2, this is our vertex. A here is positive 1. But since A is positive, then our parabola is concave up. So it's going to be something like this. We have to check the y-intercept. The y-intercept is given by f of 0. So this is 0 minus 3 whole squared minus 2. This is 9 minus 2, which is 7. So let's say that it's going to be somewhere here. Now, obviously, there are two roots, one lower than 3 and one higher than 3. So those two roots are obtained when this expression is equal to 0. But solving this expression is very easy, because consider x minus 3 whole squared minus 2 is equal to 0, yields x minus 3 whole squared equals 2. Taking the square roots of both sides, x minus 3 equals plus or minus 2, root 2, and then x equals 3 plus or minus root 2. And root 2 is approximately 1.4, so the two roots are going to be positive, but one is going to be slightly larger than the other. And if we try to sketch it we end up with this curve. The larger root is this one. It's going to be 3 plus root 2. And the smaller root is this one. It's going to be 3 minus root 2. And that's your sketch. Our second function was f of x is equal to 2 times x minus 3 all squared minus 13. Again, let's put our axes here. And the vertex was at 3, negative 13. And it was concave up. What's the y-intercept? F of 0 is 2 times negative 3 squared minus 13. This is 9, so this is 18 minus 13, and this is 5. So the y-intercept is somewhere here. And in order to work out the two roots, if you wish, that is, we can equate this expression to 0, immediately giving us 2 times x minus 3 all squared equals 13. Therefore, x minus 3 all squared equals 13 over 2. Taking the square root and adding 3 to both sides gives us x equals 3 plus or minus the square root of 13 over 2. And this will be your quadratic. It is stretched, even though with a sketch it's not very easy to show the stretch factor. It is stretched by a factor of 2 compared to the curve of y equals x squared. Obviously, this root is the larger root, 3 plus root 13 over 2, and this one is the smaller root. And finally, considering f of x equals negative 3 times x plus 2 all squared plus 7, we have our vertex at negative 2, 7, but it's concave down. Let's work out the y-intercept. F of 0 equals negative 3 times 2 squared plus 7. This is negative 12 plus 7, which is negative 5. So our y-intercept is somewhere here. Without worrying too much about the roots, we can just freely do this. And if I look at this, I find that the negative 2 is not really in the middle of the parabola. The axis of symmetry should be passing through here. So I would rather be closer. This distance should be the same as this distance because the vertex is halfway between the two roots. So more or less this is slightly better. And if you want to calculate those two roots, you can simply by equating this expression to 0, and without going through the details, x equals negative 2 plus or minus the square root of 7 over 3.